Hey everyone. Okay, I'm just trying to check that everything is being streamed. We'll yet again in the situation where I'm stupidly talking and nothing is happening. Okay, I guess something is happening there. Good. So I will also be tracking the chat here. I hope I can do it from my phone because today I'm also making some changes. I might want to use iPad to communicate about the problem. We'll see how it goes. I haven't solved this problem before. It's a relatively easy hard. And I just need to set a timer. Okay, let's go. We are given an integer array grid. So list of integers. And we can have several values there. Starting square, there is just one like this, representing the ending square. There is exactly one like this. 0 representing empty squares. We can walk over obstacles. Return the number of 4 directional walks. What is a 4 directional walk? Oh, that work on every non-obstacle square exactly once. Okay, 4 directional walks. Okay, I see. So we can move in any direction, and we are returning the number of such walks. Fine. So we will list test and challenges. So the challenge is that from each cell can move in 3 directions. So O of 3 to the power of mn runtime, right? Because then on each direction we can also choose one of the 3 directions, and then again one of the 3 directions. Obviously it will not be the case all the time, so I'm not sure if that's exactly right, but it still feels exponential. So that would also require me to check how big can be our space. So yeah, it's at most 20 by 20. So we'll recall then 20 by 20. Okay, and then tests. So let's start with something very simple. So 1, 0, 0, 2. And there are exactly two ways to move like this, right? Then let's do something a little more sophisticated. 1, 0, 0, 0, minus 1. Okay, let's, just for the sake of it, let's change this problem so that it's easier to represent it. I will call 3 representing obstacles for tests, and we'll change it for the final submission. So 3, 0, 0, 2, 0, 0, 2. And here it will actually also be 2 ways. But for example, if we change and move 3 from this place to this place, actually let me not call it 3, let me call it just minus. So minus 1, but here I will be representing it as minus, so we cannot stay there. And here it's 1, 0, and here let's move it here. So now how many ways are there? There is just one way to get here, but then for each of those positions there will be like, okay, we can go to the right, to the bottom, we can go to the bottom, to the right, or they can go to the right, to the bottom, to the right. So there are 3 options now. So, let's talk about possible solutions, shall we? Backtracking with pruning. So the thing is, right, we need to also visit all our squares. We will also have to figure out where do we start and where do we end. Okay, at least where do we start? So we might as well go over the whole matrix and calculate how many squares do we have visited and visited. So then we can try to traverse in all possible directions, in all possible ways. And if we end up on the ending square, we will add 1 to total ways, right? The problem is that 3 to the power of 400 is a very, very problematic thing. Okay, so what is the way to represent a state here? We can represent a state by storing the whole matrix that we have, m times n matrix, as tuples. So, and then we can memorize it with memorization. So the whole idea will be that, oh, actually I made a mistake here, right? Because here we can move, for example, here, down, down, right, up, right, bottom. Okay, there are 0 ways because we can never get here and get out. So that's incorrect. But something like this, okay, let's see, 0, 0, right? Is it possible to get any answers here? No. Let me write another challenge. Have to visit all cells. That's an important thing that I missed. That we don't want to just sum all the possible ways. We need to also visit all the possible cells. And then there are states that are impossible. Like we can try some state, we can get to a state, we can represent it as like all of these visited cells. And we can come to a state from which is a dead end. So there can be, yeah, we just store the number of ways from each state and how we can reach the end. And we populate this with backtracking. And it will just require a lot of steps. So how many steps will it require exactly? Okay, so we store states for each of the possible ways to arrive at some cell. But there is a smaller amount of possible ways to arrive at some cell. It can still be on the order of 3 to the power of mn, but maybe it's the issue here is that those states are not independent. All the cells are not independent. If you are visiting a state, you only can visit like one of the three items nearby. So it will be already like at most 2 to the power of n, because each cell can be either visited or not. But then visiting, if we know that any cell is visited, we know that there is at least one neighboring cell that is also visited. So realistically, there will be a limited number of cells, but I don't know how to figure out the upper bound on this. So store states for each of mn cells can have up to 2 to the power of mn states. But okay, at least we are not recalculating things for each of those. And then for each of those, if we will need to do a depth search with backtracking. And then if we find a specific way to get to the enemy, or not to the enemy, to the ending state from this cell, we add 1. Okay. So how many total operations would we need to do here? We would need to try all the possible ways to reach this ending state. So it will be still 3 to the power of mn runtime, but it will be pruned heavily. So we will not actually get that many states, and I'm not sure if we can, like, I'm sure that we can create an algorithm that will tell us if it's even possible to get any states. Because, for example, for this test case, it's impossible to get more than 0 states because it's impossible to visit this state. So you can write an algorithm that would work for figuring out whether it's possible or impossible, so whether you should return 0. But if it is possible, then you are left with only with a chance to like memorize things and try to figure out all the possible combinations. So I will now write the code. We also need to, each of those decisions will also have to do m times m operations, because we will need to store the state, and storing the state, it will be like O of m times n. So then backtracking, we will essentially be using DFS, and visited will be a matrix, but let's first say that m and n will be equal to length of read and length of read 0. So then visited will be false times n for ground in range m. Now for I in range n, we need to find the starting place. For j in range m, if read m, oh, let's not call it ing, let's call it column and row. It will be more readable. Row column equals 1. Oh no, just 1. We are not storing strings. So if it equals 1, then start row start column equals row and column. Then dfs. We pass column, we pass row, and we pass state. Okay, so let's be explicit here. This will be an integer, this will also be an integer, and this will be a tuple of tuples of integers. And then we will be returning integer and pass. So let me create a small subfunction that is generate state from visited, which is list of integers, and that will be returning tuple of tuples of integers. And it will be a simple function, return tuple of row for row in visited. Okay, so now what do we do with DFS? We will be assuming that when we are entering DFS, the column and row that we are entering from, those are already marked as visited. So we need to mark visited row start row start column is true. I'm, by the way, not breaking from here because it won't improve our running time. So I don't want to focus on that. And just breaking here will break us from the inner loop, but won't break us out of the outer loop. So it won't change much. Okay. Now, here we will do what? We also need to have directions. Will be 0, 1, 1, 0, -1, 0, 0 minus 1. Now total ways equal 0 for delta row, delta column in directions. Let me just right away do this LRU catch here. Okay, 20 minutes have passed. Let's spend an hour 20. For delta row and delta column in directions, we are trying to visit all the possible cells. So if this cell is not visited yet, if not visited, let's start with 0 is smaller or equal to row plus delta row and smaller than m, and 0 is smaller or equal to column plus delta column and smaller than n, and not visited row plus delta row and then column plus delta column. So if our neighbor is not visited yet, and finally we should be able to visit it. So it will be and grid oh damn, yeah, we also need to track the current number of visited cells. Total it will be something that we can calculate from our state, so we are not exploding the amount of memory that we need to use, but it's just convenient to store this way so that we can track how many do we need to visit total columns. So let's also calculate this here, or need to visit equals 0 if grid row column in one of 0, 1, or 2 need to visit plus or equal 1. So then we will have total visited as 1, and here when we are entering DFS we need to decide that we are visiting this particular cell. So total visited plus equals 1, and if my current column and row will be if grid row column is equal to 2, so it's an end state, and total visited is equal to need to visit, then here we just return 1. So we have just found one way to get to the end from start to end, visiting all cells that we need to visit. Okay, so now not visited and grid row plus delta row column plus delta column is equal is in 0, 2, because both are fine. Then we can actually visit this. So what do? We say first of all that visited of this is true. That's the first thing that we do. Then we run DFS. Current state will be equal to self-generate state of visited. And then we need to run DFS from this place. Oh, yeah. Ways from choosing this name will be DFS of row plus, oh, we start with column plus delta column, row plus delta row, and then current state and total visited. Then we need to update our, when we are returning here, we need to update this to false. And we need to add total ways plus or equal however many ways we have found. And then we need to return total ways. And finally, here we will need to return DFS. Yeah, I'm just thinking whether we need to pass any current state. No need, but for consistency. So we don't need to generate the starting state because we will never ever get into the starting state because we can never go back to the start. But just for consistency, we will create a state so that we are passing the correct element that we are promising here. So here and here. So we will create initial state will be equal to self generate state of visited and return DFS from start column, start row, initial state, and we start with 0 because when we start exploring our start, we will first of all add this total visited plus 1. Okay. So this sounds like something that is fully implemented, if I haven't forgotten anything important. So let's try to track something with this. One, 2, 3, 4. Okay, visited is also false. Oops. change it here. So it will be false, 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 false. But then we discover that we have start here, so this is becomes start, and also it becomes visited. I will just mark it as start for clarity. Okay, so we need to visit, we iterated, we have updated this, and then how many do we need to visit? 1, 2, 3, 4, 5, 6, 7. We need 7 to visit. And then we start this DFS, and this DFS gets to be, okay, total visited. We try to iterate over all directions. We have only one direction that we can go to, which is this one. So basically here we say that, okay, however many we get from this will be our result. Then we try different directions. Let's say first we try the right one. How do we try the direction? We check that it's inside the bounds and it's not visited yet, and it can be visited. So then we start by marking it as true. So we already marked this true. Let's mark this as true. And then we generate the state, and then we try to visit it, and then we continue iteration. So then we try to visit, let's say, this one. So we go to the top, then we go to the bottom, and we see that it's, I think, Aleph. 0. So basically, if we have come here, if we have come to an end without visiting all the possible cells, then we will never get to an end with some valid path. That's what we have forgotten in our, we have created a bug. So then we see that, okay, it's false, so we return here, and we try it here, so this becomes true, and then we try all the possible directions, we get nothing, so we return back and we return 0 again. So from here we cannot achieve anything. So let me actually go that this will be 0 possible directions, and this will give us 0 possible directions. So if we ever come to this point, we will never get where we need to be. So then we try from here to go to here, and this becomes true. And then we try, let's say, to the right, and this becomes also a no-go. And then finally we have to go here, and we have to go here, and we also see that it's a no-go, so we are marking this as 0. And then when we started iterating here, so the only way is to go down, and then it's to go right, and then it's to go right, and we haven't visited everything. And when we try to go up here, we will see that there is 0 ways, so we will just return. And essentially we have visited all our, so yes, I think I need to update my calculation. So we have visited, oh no, we have visited at least just once all our cells. But yeah, we will have to retry things again because we have visited them from a different state. So no. Previously we tried when these cells were empty, but now we are trying when these cells are filled. So we will be again trying to calculate it, so it will not be that straightforward. But overall, it looks like the correct solution. So let me paste it. Network error, okay. What is it? Oh, I have, as always, forgotten. self. Okay, it works. Wow. If I haven't forgotten self, that would have been great. And we have done everything, oops, in 34 minutes, which is good for a hard problem. Okay, there are obviously better solutions. Let's maybe see a sample of those. Maybe let's also see a tutorial. So they're also doing, yeah, they're doing the same thing, but probably just in a more efficient way. Okay, let's just check a tutorial. So if there is something, backtracking approach 1, okay, and there is just one approach. So yeah, time complexity 3 to the power of n, and total number of cells. I even have calculated this. Oh, in place technique, we don't need. That's interesting. So how are they keeping the state? They're more efficient in keeping the state. Is it backtrack? Okay, I don't know how they're tracking the state. For me, the problem was that I'm doing this LRU cache thing, right? Because we need to track where we came from and which cells we have already visited. And to track this, we only can pass tuple because tuple is immutable. And if we pass just the current state, it's a mutable thing. It won't work, according to my understanding of how this works altogether. So yeah, I will need to dig deeper into that and understand how they're storing state. For now, it looks like they don't do any kind of deeper logic, but fine. I will do that offline. And thanks everyone who have been watching. I appreciate you being here, and I hope that I'll see you again tomorrow. And maybe today, actually, I might stream something about machine learning system design.